All right, welcome back to part 2 of your quarterly assessment review. The next section is going to deal with graphing quadratic equations, and it's going to correspond to problems 2 and 5 from your review packet. Many of you, I hope, still have the foldable that we did in class one of the very first days that we started this unit, where we talked about quadratic equations and the 3 different forms of the quadratic equation. Each form has different advantages. For example, standard form is probably the most difficult form of the equation to graph because it really doesn't give you any insight into where the vertex is or where the intercepts are. Although looking at the a value, and notice how it's the same no matter what the equation shows you, the a value does several things, and we listed them down here at the bottom of the page. When a is positive, our parabola will open up. When a is negative, the parabola will open down. As the value of a, or the absolute value of a, increases, then our graph stretches and becomes more narrow. If that value decreases, then we know that our graph compresses and becomes wider. When a is equal to 1 or negative 1, then we say it's congruent to the parent function. Vertex form is a very convenient form of the equation because we can easily identify the vertex. And in this case, the vertex would be the coordinates h and k. And remember that when you have those parentheses, x minus h, that's a sort of a reminder that we're taking the opposite of the h value when we're stating our vertex. Once you know the vertex and then know the direction that the graph is opening, it makes it very easy to graph. Intercept form is also easy to graph. This is also sometimes referred to as factored form because that's the process that we use to go from standard form to intercept form. And the intercepts in this case correspond to your x-intercepts, and they're going to correspond to the values of p and q. And again, notice that inside the parentheses, it's x minus p, x minus q. And if we take the opposite of those numbers, we get our x-intercepts. And that's because essentially the x-intercepts correspond to the zeros of the function. And if I let y equal 0, then the quantity x minus p or x minus q both have to be 0. And then if I solve, that's what gives me the opposite. All right, so let's take a look at the very first problem that we're going to do. This is a non-calculator problem, so you really have to understand all the terms related to the equations. So we're asked to identify the vertex, we're asked to determine if the vertex is a max or a min, the domain, the range, we're asked to describe the dilation in terms of the skinny, stretched, or skinny, wide, or congruent, the number of real roots, and remember, real roots are simply your x-intercepts. If a graph doesn't have any real roots, it's not going to have any x-intercepts. So those are your parabolas that open up above the x-axis or down below. The y-intercept occurs when x equals 0. So if you're asked to find the y-intercept, just plug 0 into the equation or into the graph. If you're asked to evaluate a function, for example, f of negative 2, you're just letting x equal negative 2, and you're solving. And if you have a graph, you're just looking for the point on the graph. So in this first one, in the first equation, you're given 1/2 x squared minus 2. This is actually vertex form. Now notice that we're used to having x in parentheses with another number before squaring it. So think about what that number would have to be if it reduces just to x. It's going to have to be 1/2. I'm sorry, it's going to have to be 0. So that means that inside the parentheses is x minus 0 squared and then minus 2. And just remember, if I subtract 0 from x, I get back that x that I started with. But when I write it this way, it makes it a little bit more obvious what my vertex is. The vertex is simply going to be the point 0, negative 2. And it's going to help to actually sketch a picture of this graph. So if I think about where the point 0, negative 2 is, the x coordinate is 0, my y coordinate is negative 2. So there's my vertex. I can tell from my a value that the graph opens up, and because it's 1/2, I know that it's also going to be pretty wide. So I can sketch my graph. And that'll enable me to answer a lot of these questions. So I already know the vertex is at 0, negative 2. And if I look at the graph, I can tell that it's the lowest point on the graph. That makes it a minimum. some of you guys were looking at the direction that the graph opens, and so it opens up, and so some people were calling it a max. But remember, a minimum is the lowest point on the graph. A maximum, by definition, is the highest point on the graph. And so in this case, since our vertex is the lowest point, it is considered a minimum. The domain for every single quadratic function is all real numbers. And the range is going to depend on your vertex. So notice my lowest point here is at -2. All of my y values are larger than that because my graph is going up. So I'm going to say that y is greater than, and don't forget your equal sign because it could actually equal -2. We're talking about the dilation. Because it's 1/2, I know my graph is going to be wide. Sometimes we call that compressed because we've kind of smushed the y-axis. And the number of real roots, the number of x-intercepts, I'm just counting them. I can see that there are 2. The y-intercept, where does the graph cross the y-axis? Well, it's actually pretty obvious where it crosses the y-axis, but if it wasn't, you can simply plug 0 in for x. And so if I do that, that's just going to give me 1/2 times 0 squared minus 2. Well, 0 squared is 0, and 0 times 1/2 is 0. So this is just going to leave me with a y-intercept at -2, which I can see on the graph. It's right there. If I want to evaluate my function at -2, again, I'm letting x equal -2. So I'm going to plug it in. I've got 1/2, and then in parentheses, -2, the quantity squared, minus 2. Don't forget, when you're squaring a negative number, it becomes positive. So this becomes 1/2 times 4 minus 2. Don't be intimidated by the fractions. You know what half of 4 is. It's simply 2. And 2 minus 2 is 0. So this is a problem that you have to do without the calculator. And it's something that you are quite capable of. All right, so that takes care of all the characteristics for the first function. In the second function, you're given a graph. So this time, we can use our graph to answer all the questions. I think it's pretty obvious that our vertex is going to be at the point -3, 0. It's asking, is it a maximum or a min? It's the highest point. That makes it a maximum. The domain for all quadratic functions is all real numbers. And this time, since I have a maximum, I know that my range is going to correspond to all the y values that are less than or equal to whatever that maximum y value is, which is going to correspond to my vertex, which is 0. In this case, when I'm asked about the dilation, the easiest thing to think about here is if you know where your vertex is, if you go to the point that's directly across from it, like so, if I go down 1 over 1, the fact that I'm going down 1 over 1, or if I were going up 1 over 1, that would tell me that the graph is congruent to the parent function. And then it would also help me identify if the graph is narrower or wider than that. But this one is congruent. The number of real roots, again, we're looking at the number of x-intercepts. And even though my graph doesn't pass through or cross over the x-axis, it does touch the x-axis at the vertex and then turn back around. That tells me that we have 1 x-intercept. And if you remember from our other lessons, that means it's a double root. And we'll need that for our next unit. The y-intercept, where does x equal 0? Well, I think about my value of x equals 0, that brings me to this point on the graph. And I can just look at it and see that my y-intercept occurs at -9. Evaluating the function when x is -2, I'm just going to go over to my x-axis, find -2, and then locate the point on my graph that corresponds to it. And I'm looking for the y value now. Well, at -2, the y value is -1. Okay, and so I've identified all of the characteristics to both the function written as an equation and a function displayed as a graph, and we can complete the table either way. All right. We have one more equation, or I'm sorry, one more problem from our review guide that deals with the graphs of quadratics. And this time you're coming up with an equation to match certain characteristics. So in number 5, it says to write an equation in vertex form. And again, remember, vertex form includes the value of the vertex for a quadratic function with the following characteristics. So we know that it has an absolute maximum. We know that the axis of symmetry occurs at x equals 4, and we know that it has 2 real roots. The first thing I would suggest is to draw a picture of it. So if I know that it has an absolute maximum, that means it has the highest point, I know my graph has to be opening down. If it has an axis of symmetry at x equals 4, I'm going to locate x equals 4 on my graph, and I'm going to go ahead and just draw my axis of symmetry. I know my vertex has to be on that line. And so I know that the x value of my vertex has to be 4. That gives me my h value. So h must also be 4. So I know I want to construct a parabola that opens down, and I know it has to have 2 real roots. So that means that it has to cross the x-axis, because 2 real roots means that it has 2 x-intercepts. So that must mean that my graph has a vertex above the x-axis and opens down. So that's what it would have to look like. And so a lot of this is going to be, your answers can vary. So in terms of your vertex, you just need to make sure that your x value is 4 and that your y value is some positive number. And it can be any positive number, really. The other thing you need to make sure is that your a value is negative. And again, it can be any negative value. It doesn't matter which one. So one possible equation would be that y is equal to, I'm just going to do -1 for my value of a. I'm going to do x. Now, even though my h is positive 4, when I put it into the equation, it'll be -4. I need to square it. And then I need to make sure that my k value is positive. So I'm going to do +2. I could also do y equals -50. X minus 4 squared plus 200. I could do y equals -0.01. X minus 4, the quantity squared, plus 1.2. And that would also be okay. So what's important here is that this number is negative. What you have inside your parentheses is x minus 4. And the number out here is positive. And as long as those characteristics are true, then you have an equation that meets those characteristics. Now, what about if I were to say, instead of having 2 real roots, what if the roots were imaginary? Well, that would mean then that my parabola would have to open down below my x-axis. It would have to look something like that. So with 2 imaginary roots, my a value is still going to have to be negative. My parentheses are still going to have to show x minus 4, the quantity squared. But this time my k value would have to be negative, and it could be any negative number. Okay? All right, that's it for the second tutorial. I'll come back in a few minutes and help you with factoring.